Here's another example using Kirchoff's laws with a bunch of batteries and resistors. So I have this circuit shown. I'm told that the switch here starts out open, and when that's the case, the voltage difference read by the voltmeter is 12 volts. So here's the voltmeter, so it's telling me that the voltage drop across this 40 ohm resistor is 12 volts, okay? And I want to know what is the EMF, the voltage difference created by this EMF across the terminals here. Okay, so the first thing I'm going to do is try to get a handle on where the current is flowing. If I'm given this, say I have this picture in a textbook or something, the first thing I do is on my large blank scratch paper is redraw the circuit myself, so I get a feel for where everything is. And so now where is the current flowing? Okay, so there's no current here in this branch. Because the switch is open, so no current can flow through a broken circuit. And so the only battery then that's contributing to the flow of current is this one. This 25 volts is the 25 volts here isn't doing anything. It's not connected in an active loop with the switch open. So I'm going to say the current then is going to flow this way in this branch, and then it's going to come to this junction and then split in two directions. And so this is going to come over here and then around here through this resistor around the other side. Remember, an ideal voltmeter doesn't draw any current, so there's no loop here with the voltmeter. It's for an ideal voltmeter, it doesn't participate. So this comes around here, and then it'll go back, and this current comes around this way and comes back. So I have sort of three different currents. I have, so let's call an I1 that's going through this middle branch. We'll have an I2 that comes out this way, and I3, the I2 that goes to the right, and I3 that goes to the left. Okay, so I can identify, say, a junction here where the current in is I1 is equal to the current out, I2 plus I3. Okay, I sort of see that ideally. And so what do I know? What can I do with this? I got a good idea where the current is flowing now, and I want to find this EMF. Okay, the other piece of information I have here is that I'm reading 12 volts on this voltmeter. What does that tell me? Okay, well, it's telling me the potential drop across this 40 ohm resistor, and so I think that might be useful information. And so that is telling me that a potential drop of 12 volts is equal to the 40 ohm resistance times the current that's going through that resistor. And that current I've identified is I2. And so I can immediately use that information to tell me what I2 is. I2 is equal to 0.3 amps. Okay, so that's useful information as well. Okay, so I think let's choose a loop. The most obvious loop. I don't know if there's an obvious loop, but the one I'm going to start with then is I'm going to choose this loop here. Color that I'm going to choose this loop, this big loop here, just because it happens to contain I2. That I know, and E that I don't know. Okay, so I'm going to go this direction with the current, and so starting with EMF, so I get a positive drop due to that potential difference. I'm going with the current through this first resistor, so I get a negative potential drop, so that's 20 I1. So now I'm coming around here. Now my current is I2. I'm going with the current, so I get a negative potential drop of 30 I2. And I keep going. The ammeter, of course, has no effect. Come through. Now I'm going with the current, and I get minus 40 I2. this, and then there's nothing else. All the way around, I'm back to the terminal. And so the sum of all of those potential drops is equal to 0. And so what do I find? I can simplify a little bit. I have this minus 20 I1 minus 70 I2, 0.3 equal to 0, and so I get E minus 20 I1 is equal to 21. Okay. And so here, I have my one unknown, but I still have another unknown. So here's this is equation 1. And so here's a good example where typically when you're solving physics problems, you don't like to plug in numbers. You like to wait to the very end and then plug in numbers at the end. I find with Kirchoff's laws problems, if I've got 4 different resistors and a couple currents, I'm plugging those numbers in right away. It simplifies what I'm doing, and it's in fact easier to keep track of what's going on. And so there's no real hard rule. That's a rule of thumb. You like to wait till the end to plug in numbers, unless doing so makes your expressions so complicated that it's harder to solve, which can happen with Kirchoff laws problems. All right. So we've got a nice relationship here, but it's not sufficient. We have to do more. Okay, so let's look at this other loop here. The small loop. I'm going to go the same direction. I start with my my EMF, some space, EMF, and then minus this 20 I1, going with the current here, but now I'm going to careen off to the left here, following I3. It has got a potential drop here, going with the current of 60 I3. And then around, nothing, back where I'm started. That's equal to 0. In fact, if I were to rewrite this, I get E minus 20 I1 is equal to 60 I3. Well, that's interesting. And so if I look at I1 and I2, I have E minus 20I on both sides. So if I subtract 2 from 1, I'll do this here, I get E minus 20I minus E minus 20I, that's 0. And then I get 21 minus 60 I3. So I can solve for I3 immediately. And so I3 is equal to 21 divided by 60. Well, that's 7/20ths. Or I3, where am I? I3 is equal to 0.35 amps. Okay, I just sort of, I could see immediately that I could solve for another one of my unknowns, and so I went ahead and did that. Now, can I use that anywhere that to be able to solve? Well, so at this point, we want to take stock. Okay, so I know I have I3, I have I2. Here's some relationships with my unknown, E, but they require I1. Both of them require I1. So I need I1, but I can do that now, right? I've got I2 and I3, so I can solve for I1. And once I get I1, it looks like I can use either of those to be able to solve. All right, so let's create some more room here. We can go back up if we need it. So I1, we knew was I2 plus I3. So that's 0.3 plus 0.35, 0.65 amps. And so now we have E minus 20, 0.65 is equal to, well, what should we use? We can go ahead and use this one. There's 21 right there. It's equal to 21. And I can go ahead and solve that. And I find E is equal to 34 volts. All right. And so there's my E. So let's add a second part to this problem. So the switch was open. What is E? I found it. Okay. And so now I'm going to ask the question. I'm going to flip the switch. Fine. What is the current? All right. So I got myself some more space here. And I'm back to the question, so I flip the switch. And so I make the connection here. I'll draw it. And now I want to know what is the current through the ammeter. Okay, well, I've got lots of, the approach the same thing again. So we have current flowing and all of that. And so let's go ahead and choose loops and current junctions and all of that process again. Okay, if I start with, what about this loop right here? This is sort of an obvious loop to choose because it in fact contains my ammeter, and so we can go ahead and try to do that loop first. So if I go that this drives current this direction, and so I have a 25 potential drop across my battery that's now connected in a loop. The ammeter has no effect. I have a voltage drop here, 40 times this current. We can call that I2. Again, that's what it was before. Then nothing, nothing, and it comes back to where I started. That's all equal to 0. It looks like I'm done. I can just solve that. I2 is equal to 25/40ths, or 0.625 amps, and that is the current going through the ammeter. I'm done. So wait, what about these batteries and these resistors and all of that? Well, they all play a role in the circuit, but Kirchoff's laws say the voltage drops around any loop have to be 0. And so this loop gave me everything I needed to know, and I've solved the problem.